So the idea is to show you or to show you what we are doing precisely in terms of addressing how to verify the properties, the security properties that we are now sort of used to rely on with the physical network infrastructures can hold as well in the case of a virtualized network. Take into account that this is important that we are not any longer able to base security, as is there in this photo, of what is normally everybody in networking has base security. That's the core equipment, the real infrastructure is behind, a tall, not very friendly, and usually armed guy. Just you can translate it into more formal terms, is that in physical access control. Not any longer functions are going to be moving around. They will be based, very likely, the future network architecture as we foresee it is much more like the bottom part than in the top part. In the top part, for those of you familiar with 3GPP, you will recognize the EPC. Down, what we have is basically an infrastructure that is built about many different interconnected clouds of different sizes, of different locations, but managed in a consistent way, and basically functions that are moving around, and not any longer you can rely on this physical access control to the key parts of the infrastructure. And this is the case. We have completely altered security procedures when we move into virtualization. First of all is that, you have to consider a relayering. The network that was at the base or at the bottom slices of the layer diagram, they become applications themselves. And you have always the combination of SDN and NFV. It's not only that you have to deploy functions, it's that you have to control them, and you have to control them in a way that is consistent at both levels. At the infrastructure level, in which you are still needing a networking principles, and at the service level, because you are building service by combining applications. So you have to start with, you have two different layers in which you have to be considered, and you have to be concerned. And then the maintenance cycles, we are talking very much about DevOps, we are talking about CI/CD, etc., but that implies that the cycles are much shorter. And the current ways of verifying the physical thing that goes to the physical place that is protected by the armed guy is not any longer the case. We're talking about deploying software and, having the way in which we deal with is that it will be through patching, through DevOps, not any longer by making the whole verification and moving the thing and making installation, and we will start to be suffering. And this is something that we have to acknowledge, the danger of zero-day vulnerabilities, because we will be layering our network infrastructure on software, more or less general purpose software that will be suitable for attacks. And this is a list of the different other risks that are derived precisely from the fact that we are losing this control by physical access control. And there are some additional, you think about it, this has been traditionally solved by cryptography, by deploying highly secure protocols, by encrypting, by requesting certificate-based access, etc. But then you have another problem, that is precisely how do you deal with key revocation in networks of the size we are thinking about? How do you deal with key revocation when you have several thousands of cloud sites? You are not controlling, or how you rely on that your key management procedures are robust enough to follow functions that are being migrated from one location to the other, or how you deal with something that is a general problem, but again is aggravated by the size and the diversity of the network services, which is how you deal with the key distribution when you're dealing with software images. So, for this, we have verifiability, and it's not that we have solved all the problems with verifiability. This is a set of challenges, as I was saying, but we have started to address some of them, and in particular, when it comes to attestation, So the capability to be reasonably sure, you're never completely sure of anything in this world, but reasonably sure that you can rely on the infrastructure and the software you're using. The guarantee that you can run, if we are talking about, I remember this morning the talk from Verizon about the collaboration with your customers, etc. The possibility of, ensuring that non-repudiation happens, so nobody can tell you, no, I didn't ask for this, or the other way around, no, you didn't send me the acknowledgement, etc. It's something that can be done. And this is essential not only for the orchestration, but as well, if you think about it, for DevOps as well. And something that is very close to my heart, because I've been working on this for a while, is in proof of transit. How you can show that you're going through the appropriate networks, the appropriate functions when your functions are virtual, are moving around, and you cannot look at the cable that is connected to the box. Well, at the station, this is a formal, I will go fast over this. This is a formal declaration of what attestation is. And attestation is based, and it's something that is well known in the physical computing and in virtual computing as well. And it's something that is what you do is that how you can rely that where you are running and how you're running on it is trustworthy, is based on a set of measurements that are made by trusted components, and what you do is that you start with a base measurement at the, let's say, the physical infrastructure level, and you go up by signing and including the previous signatures. So what you create is a complete set of measurements that you compare what is normally called the golden measures, that is hosted somewhere in a trusted repository, so you can verify the measurements you have received, that are properly properly signed following a chain of trust, and you can compare them with your golden measurements, so you can be reasonably sure that you're going to run your functions on a trusted hypervisor that is running on top of a trusted operating system that has been installed on top of a trusted machine. So challenges, well, it's about how you attest network topology. People are working on that. We have some initial results. Runtime verifications, runtime means that after the boot, you keep checking, or well, again, scale. We're talking about huge deployments, very highly distributed clouds. No, we're not talking about a a dozen or even 100 sites, huge sites, but we're talking about something much more complex. This is something that we have been working inside the NFV and inside the ETSI NFV group, and there is a document that is NFV Sec 7 that defines something that, as I said before, you cannot never be sure of everything, but you can have a certain level of assurance, and we have defined this 7 level of assurance. If you're interested, this is the graphic that you have in the document, and if you are interested, search for NFV Sec 7. Well, Sec 007 as Bond. James Bond in your browser, and you will have it. Non-repudiation. Well, when it comes to non-repudiation, is the idea that we are moving from the fully which is monolithic, the full monolithic environment in which you own the infrastructure, you own the software, you own everything, even that you're providing to your customer, to a principle in which what you have is different actors that can provide services, and you are using the services of others, whether you're a customer or not. Even that happens even inside the operator itself. And that implies that you have several ways of relationship among different operators, inside the same provider, or even what is much more important, even operational, if you're thinking about DevOps. When it comes to the horizontal and the vertical dimensions, whether you are asking for something to another operator, or you are making a request to an infrastructure or function provider, basically normally what you're using are APIs, a request response protocol. This is the method that we devised in a project precisely for virtualized interdomain mechanisms that I think are fully applicable as well when you're talking about the kind of requests you send to your infrastructure or function provider. And the idea is, as you can imagine, you derive a fingerprint, you sign the fingerprint, you wrap it with your request, you send it to your to the responder. The responder prepares the response, including precisely the fingerprint you sent, signs it again, generates the fingerprint, signs it again, send it back with the response, and both parties, both the requester and the responder, store them so they can be checked for further audits or whatever is required. What is interesting is that this can be applied as well if you're using DevOps. Because as long as you apply something that is essential, that is the possibility of mediating the DevOps requests. That is what allows you to have an auditable trace of the updates and of the different changes that have been applied to the infrastructure. This is the diagram of another project we were in about precisely this integrated DevOps, in which what you have on the one hand is that the developers they have an SDK, a service development kit, that allows them to assemble the whole service and the whole changes that are going to be deployed on the service platform. And you have something that we call the gatekeeper. You can call it whatever, or you call it a general mediator or whatever. So the idea is the gatekeeper is precisely making an initial verification of what can be achieved or not. And the important thing is that at the end, that becomes essentially the same case of a request-response protocol. So you can generate the same traces and any change in your infrastructure by means of DevOps made by your own developers or by the third-party developers is auditable and traceable. And finally, as I told you, proof of transit. You have something that is virtual and you want to prove, and this is something that was a direct request from customers of ours. It's not that we have invented this as an academic exercise. It's that you want to prove that traffic is flowing the right path and is going through all the functions that it is requested to do. Traditionally, and I was told by these customers that traditionally this is something you had your audit and somebody came and checked that the orange cable on the one side was connected to the other side correctly because you could follow the orange cable or you could follow the blue one. Now everything is virtual, everything's moving around. How do you prove that? And well, if it's not, you make it verifiable by third parties for the audit. And well, the idea is you think about it, it's natural, it's about you provide some cryptography into the metadata to prove that you can transit. And for sure, normally this should be applicable to flows of several hundred packets, but you can have to be sure that all packets, so you have to apply this per packet, though you can record this per flow. Well, people have been working on this. We have been working on this with a university. I know there is, and because I've been discussing this with some other colleagues in the ITF, and the idea is to use secret sharing. Basically, the idea is that each individual function has a secret that combined, as appears at the end, that combines, allows you to open and to verify it. There is an ITF draft on this that we are still working in enhancing it. And we have been working precisely as well on level of assurance, so you can get coded to the nature of the secrets and shares. You can have several levels of assurance, even, for example, having it order or unordered. You can be sure that all packets went through the correct functions in the right order, or only to be assured that you were through all the functions, but not to have a guarantee of the order. And well, originally the talk was going about to be blockchains, and this is where blockchains come into play. I'm not going to explain you what a blockchain is. If you don't know it, Google is your friend, Google it, and then good luck, because probably the explanation will not be very clear, but basically the idea is that having a distributed ledger could help in the case of the attestation precisely to provide verification guidance. You can publish it in a way in which everybody will trust it without having a central authority. A common store for node repudiation. We're talking about the requester and the responder to have separate logs that can be compared. If you store in a distributed ledger, everybody could verify it in a single place. For sure, a secure record of flow transit, and would be extremely interesting for using smart contracts, though, mind you, we are not talking here about cryptocurrencies. We're not talking about creating a cryptocurrency on the network. Simply having a distributed ledger, and this is why we're not talking about blockchains. is a distributed ledger. We're applying the same cryptographic principles in which blockchains are based, but not necessarily talking about a cryptocurrency. And well, there is a need to allow this. What we need is a way of openly operating these distributed ledgers so we can run at the network scale. And well, basically, just just for you, do you know what this is? This is the ace of gold in the Spanish card. Exactly. And that's why I will say everything is, if you look at it, everything is about ACE, is adaptability, availability, assurance at the station, accounting, access, etc. And this is where the ACE of gold relies in precisely expanding this, about having better metadata, for example, well, for sure, enhancing computational efficiency, because this is critical when it comes to crypto. We are making some experiments right now with quantum key distribution to enhance crypto and to achieve this scale we were talking about before. Thinking about the integration of the different technologies, and this is why, for example, proof of transit could be used for attestation. If you show a proof of transit of an operational packet, you can show that the topology is what you expect it to have, or APIs that are affirmed by attestation, so you can rely more on what you're doing with your responder. And well, we are thinking about other ideas and that are more related precisely, if you allow me, with ideas that are connected with the application of cryptocurrencies, etc., which is precisely accounting for function providers, or the access, how to count on the access for third-party services. And that's all. Thank you. I don't know if we are over time.
Any questions? Why don't we take at least one question? While they're collecting their thoughts, one thought I had was you were going through there, you can't do it at the flow level, you need to get down to the packet level. What do you think the impact is on network performance?
No, that's true. It's something that's why we are defining several levels of assurance. If you have, this is one of the reasons that this morning, I don't know if you were here this morning during the Nokia presentation, I was very much interested in whether they were using crypto or not for the, if you're using crypto hardware accelerator, the impact should not be that serious. If you're not, well, good luck. So, and for sure, this kind of, and the reason why we have defined this levels of assurance is that precisely in the case that you need a high level of assurance, probably it's not that you don't have a performance assurance penalty to pay, but the problem is that you will need a much more expensive equipment. So it's about nothing, as it was shown in some TV series, what about that magic comes with a price. So that's it.